Okay. So welcome everyone to our popular STEM Talk series. This is the second talk this semester, and we have a very special guest today. But before we introduce her, let me just tell you the popular STEM Talk series is sponsored by the GCC STEM Initiative, and this special talk is also sponsored by the Honor Society. And the Director of the Honor Society wants me to make a couple of brief announcements about a visit here by Steve Gadsden. He's going to do poetry readings of all the campuses between March 31st and April 1st. So be sure not to miss this. And then we have the William Georgia Shakespeare Touring Company is also coming to the GCC campuses and is going to perform William Shakespeare's Romeo and Juliet. So be sure to check the GCC web pages for up-to-date information on these things. Okay, and now I'd like to introduce our speaker for today, Dr. Laura Greene. And she is the Swanson Professor and Center for Advanced Study Professor of Physics at the University of Illinois at Urbana-Champaign, and the Associate Director for the Center of Emerging Superconductivity. And her research is in experimental synthetic matter physics, working to elucidate the mechanisms of unconventional superconductivity and developing methods for predictive design of new castings of superconducting materials. That's a mouthful. Okay, well, giving a whole bunch of very important positions and straight to the awards that are super stuff. So her awards and honors include a Guggenheim Fellowship, the E.O. Lawrence Award for Materials Research from the U.S. Department of Energy, the Maria Meyer Award from the American Physical Society, and the Belcourt Award of Excellence. So, we have a very important and very well-known speaker here today. So let's give her a warm welcome. I'll turn the stage over to you.
Okay. Thank you very much, Ricky. That's a very nice introduction. It always is a little bit scary to have to introduce. I want to thank Ulrike and also Professor Ray, who is here to help facilitate this, and my sister, and it's just a real pleasure to be here. So today I'm going to give you more of a general talk on high-temperature superconductivity. And the title is actually called Taming Serendipity. And it's because I'll go into the history of design of superconducting materials, or the lack thereof, because all the discoveries have been quite serendipitous. And this is the things I'm going to touch on during the talk. This is a symbol for our center. It's the Energy Frontier Research Center of Superconductivity. And the applications of superconductors are these three right here. For power transmission, as an electrical carrier, for wind generation through wind power, and also this is something called SMED, the superconducting magnetic energy storage. And I'll mention that a little bit at the end. But superconductivity can have a tremendous impact on a renewable. What I focus on here would be design of the superconductors, and you search through periodic tables to find these things. And I'll present some of our design principles. And over here is recognizes some of the mechanisms. It's called the carrying mechanism of electron CCS. And I'll touch on that through the talk. And during this talk, I more than welcome you to interrupt me if there's a point that you would like me to expound on or you don't understand. I would much rather not get through all 700 slides and be able to answer some of your questions. So I will introduce superconductivity and type 1 and type 2, the need for new and better superconductors, as I mentioned, the serendipitous discovery of superconductors, towards renewables. Our new ideas and new famous divisions from material design, some are not, but we just wrote more proposals to try more things. And then what I probably won't have time to talk about is, again, I've got a couple of graphs of my own research is something called point contact spectroscopy. And that's been very, very, what we didn't expect, very useful in trying to identify candidates for new high-temperature superconductors. So let's start out with the temperature scale. What we use in physics typically is the Kelvin scale, where boiling water is 370 degrees, And
I 273.
it's just the centigrade scale shifted by 273 degrees. Now, the conventional superconductors, and I mentioned those before, I know I haven't defined it yet. In the old days, you had to cool them very, very cold, and you needed to use liquid helium, which is extremely expensive and difficult to get, and that's gotten worse and worse through the years. Now, the new high-temperature superconductors are above this temperature here. So this is up to 30 degrees Kelvin. 77 degrees Kelvin is the temperature of liquid air. So instead of being something that could be $20 a liter, $50 a liter, the price is skyrocketing. Liquid nitrogen, liquid air is cheaper than beer or milk. And so it's very cheap to cool these things. And the high temperature superconductors are still pretty cold. They're up to about 165 degrees Kelvin now, but they're much easier to cool, and therefore they're much more popular for applications. So here's a very famous plot that was in a report we wrote for the Department of Energy in 2006, and it's TC versus time. And I know I haven't defined TC yet, that's coming up, but this will give you a picture of the revolutions that's happened in the material. When I go through the history, I'm going to start here with this thing in 1911, where mercury was discovered as a superconductor. And by the way, there's breaks in this plot. This would be a pretty linear plot. And I will talk about how all these superconductors up to magnesium diboride are all conventional superconductors, and we know why they superconduct. There are many, many other families of superconductors on this plot, and we don't know why. We have clues and we have ideas, but we don't exactly understand why they superconduct. During the course of this talk, I'm going to tell you how these conventional superconductors work, and that's what the Navy discovered. These are the high-temperature superconductors. In 1986, they were discovered and pushed above liquid nitrogen temperature. And a few years ago, in 2008, a whole new class of superconductors were discovered called the iron-based superconductors. And that was pretty exciting. So what is a superconductor? Okay. There are two defining properties. Number one, below a certain TC, critical temperature, it carries electricity with zero loss. And I'll say that a few times because it's really weird. No resistance. Another thing is it's a perfect anti-magnet. And I'll show you why that's a great application here. Another thing, which isn't really a defining property, but it is a property, is that there's long-range quantum mechanical order or phase coherence. And I'll define that as I go along, what that exactly means. This is what we mean by zero electrical resistance. This is the resistance, that's a figure for resistance, and this is temperature. And in most metals, as you reduce the temperature, the resistance goes down. At high temperature, boiling water is moving around like that, and the whole lattice is shaking around. And as you lower the temperature, things start calming down, and the electrons can go through the material much more easily. And that's why you have this resistance drop. But very abruptly, in a superconductor, the resistance goes to zero. What does that mean? Okay, so here we have a picture of a space heater, which we know very well in Urbana, Illinois, and now you're getting to learn those in Atlanta. And what we have here is space heaters. If you've ever looked inside, has anybody ever seen a space heater here? Okay. So the inside of the space heater has these very hard, dark, rough wires on the inside. Those are designed to have very high electrical resistance. They're attached to the wire that goes into the wall, which is a thick copper cable. The wire, if everything is working right, the space heater coils get hot, and the thing plugged into the wall, this cord here, stays cool. Why? Because of the difference in resistance. A copper wire has very low electrical resistance. The wire heater has very high electrical resistance. And that gives you the amount of heat dissipation. So if you can think about if you're rubbing your hands together, if you've got cream on your hands, it's not going to get very warm because you have less resistance. But if you rub your hands together like that, you can really heat up, and that's because of the resistance. And it's kind of like that with an electron. If it's bumping around, it feels a lot of resistance, and it dissipates heat, just like when you rub your hands together. And so the copper wire has low electrical resistance, so there's very little heat dissipation. A heated wire gets hot because there's a lot of heat dissipation because it has a lot of resistance. And this is what happens with the superconductor. Okay, zero electrical resistance, it dissipates 0 heat, which means if you have a battery in Atlanta and a light bulb in New York City and they're connected with superconducting cables, you don't need any power station. There's no loss. So you can imagine how important that could be for energy. I'm still defining a superconductor now, and another very interesting property is something called the Meissner effect. It's actually the Meissner-Aschenfeld effect, but Aschenfeld was a graduate student, so we know how that goes. Okay? And so below the critical temperature, this is when they realized there was something really different about a superconductor. It's not a perfect conductor, and I'll say that again in the next slide. It does something really weird. In a normal metal, you can send magnetic fields through a normal metal. In a superconductor, below its critical temperature, the magnetic field is completely expelled. That's what we mean by anti-magnet, and the science term is diamagnetism. And there's two kinds of superconductors. There's a type 1 superconductor and a type 2 superconductor. Okay, the type 1 superconductor is what this is here, and at below a certain temperature, all of the magnetic field is ejected from the superconductor. And so we have the amount of field as a function of temperature. Here we have below a certain critical field and below a certain critical temperature, the material is superconducting. Now, just like if you raise the temperature, the material goes normal. If you put on too much magnetism, the material also goes normal. A type 2 superconductor, which Ulrich understands here, work on this stuff, this allows some magnetic flux penetration. And what we have here is you will get little vortices that go in here. So you have your superconductor, you put a field on it, and some magnetic field penetrates. Okay? Most superconductors are type 2. Anything that isn't a simple element is a type 2 superconductor. And it has these vortices. And what happens is the magnetic flux penetrates, and there's supercurrent around the outside. But the inside where the magnetic field penetrates is not superconducting. So if these vortices can move around, they're going to dissipate power, dissipate energy actually, because they're not superconducting. So one thing that's really important for applications is find ways to make sure those vortices are pinned. And a lot of our research is trying to pin those vortices. Just to show you very quickly, a superconductor is not a perfect conductor. If we take a superconductor, okay, and we put it in a magnetic field, and we cool it down below its superconducting transition temperature, the magnetic field is expelled, and if you remove the field, you just have a chunk of metal. For those of you who have had any physics at all, you will follow this. In a perfect conductor, if you lower below a certain temperature where it becomes a perfect conductor, not a superconductor, the magnetic flux is not expelled. In fact, Maxwell's equations say in a perfect conductor, you can't move those flux lines, so they get pinned inside. So if you remove the external field, you're left with something that acts like a magnet, because those magnetic field lines get pinned inside of this perfect conductor. So we see here that the final state is different if you have a superconductor or a perfect conductor. Okay? Now, this is applications of diamagnetism, and this is kind of cool here. We see that it flows. It doesn't matter what direction it is. There's currents that go around there that are expelling the magnetic field. Pretty cool. We do this. I didn't bring the nitrogen with me, but we play with this all the time. Well, I'll show you another one. And there has been superconducting levitated train. There's a reason you want to do this, because you saw how this is the magnet, and this is the cool superconductor here. And what happens is you can see that it's stable. Two magnets. If you try to balance two magnets on top of each other, that's inherently unstable. It's called Harshaw's theorem. So you have to mess around to make magnetically levitated trains. But we can see it has to do with these pin vortices, that this is quite stable. Now, the Japanese built the first magnetically levitated train using a superconductor in the 1960s, using conventional superconductors. And they would tell me the same story over and over again. It only went a kilometer, but it went far enough to take our funding agents for a ride. So that's But now there's more and more of these levitated trains. I've been on a conventional levitated train and prototype superconducting levitating trains, and the Japanese are now building a levitating train based on high temperature superconductors. So I have a little funny play here, and I will.
Ladies and gentlemen, from the physics department at Ithaca College, Dr. Matthew C. Sullivan and the quantum levitator. This is a quantum levitation track, correct? It is indeed. All right. Well, thank you so much for coming on to help me crush Jimmy with quantum levitation. As I'm sure you know, quantum levitation refers to the phenomenon whereby the magnetic flux lines flowing through a type 2 superconductor are pinned in place despite the electromagnetic forces acting upon them. I learned that from the inside of a Snapple cap. Dr. Sullivan, can you confirm that if my ice cream quantum levitates, it is undeniably the ice cream of the future? Absolutely. That's just science. Here we have some of my American Greene. It's available in mini cups, which Jimmy's is not. Okay? And I will confirm that it is delicious. And now, are you ready to send my ice cream into the future? Certainly. Okay. Ice cream of the future. Engage. Okay, it's levitating. Eat it, Fallon. Eat the future. We'll be right back. Hit it.
Well, thank you, Stephen. So yeah, that was really fun, and I've had students build those tracks and everything like that. They're great. They're just really fun. And the first application of high temperature superconductors was actually education, where people could actually see this levitation happening. It's really quite amazing. I still get excited when I see it. So long range, quantum mechanical order. What's all this about? This is what happens inside of a superconductor. We call this a correlated electron problem, and this is the only solved correlated electron problem in physics. I've been doing correlated electrons almost my entire adult life, and the field started in 1952. Okay, and the first proof that of the existence of these correlated electrons was 1973. This is not a solved problem. This is the only solved problem of correlated electrons. The electrons fall into a single quantum state. Let's assume this is a metal. Okay? If this is a metal, there's about 10 to the 23 electrons in here, right? Each electron has an equation of motion, which we call the Schrodinger equation. So you can write down the wave function for each of these 10 to the 23rd electrons. E to the ikx minus omega t plus phi, right? That's good. So you need 10 to the 25th. If you take this material that below a certain temperature superconducts and you cool it down, you don't need 10 to the 26 wave function. You need 1. That's the BCF wave function by Dean, Kugel, and Schrieffer. That means that all those electrons are in some kind of step together. They act as one set of waves, and it's one single quantum state. A little background here, okay? This was why it was so amazing. If you know this, fine. Otherwise, I'll tell you for the first time. Electrons aren't allowed to be in the same quantum state. They're called fermions. They have an intrinsic magnetic moment. It's half integer. Forget the details. Physics dictates, and we know that no two electrons are allowed to be in the same quantum state at the same time. Plus, electrons are all negatively charged. How do you get them all to go in the same quantum state where they're all going to push each other away because they're all negatively charged? It was joked, you can't repeal Coulomb's law. How do you get it worked out? And that was the genius of Leon Kepler. He figured out a way for the electrons to pair up in something called Cooper pairs. And I'll describe that later on. But if they pair up, they are no longer half integers. They become a single integer. And things like that are single integers are called bosons. A photon is a boson. There are other things, and those are allowed to fall in the same quantum state. So they had to figure out how to do this, and that was the genius of Greene, Cooper, and Schreiber. And they're called Cooper pairs. And that was like 3 buildings away from where my office is, the University of Illinois. Brilliant history. It was fantastic. The way that they think of it, there's this mattress analogy that people use a lot. And that is that even if these two people don't like each other, if the mattress is soft and squishy, okay, they will fall into the center of the mattress. Okay? And so it's not paired because they're attracted to each other. They're paired because the area surrounding them is squishy and they fall into the center. To think about what's going on in a conventional superconductor, instead of a mattress, we have a ladder. And we can think of these as niobium nuclei, because niobium is a superconductor on the periodic table, which I really like. And what happens is below a certain, at high temperature, of course, these, just like I said before, the atoms are moving around, the nuclei are, high temperature, yada, 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 and you cool them down, okay, and they stop moving so much. And what happens is there's a strong electron lattice interaction. This electron can go through here, and it causes the mattress, the lattice, the ions to fall in together. And it's created a net wave of positive charge. And that electron at a later time sees that net positive charge and is drawn in there. So this, we can carry this, all analogies break down, I'm pushing too far. But what I can make the mattress analogy a little bit better, saying that these two people really don't like each other. So one is in the center of the mattress, and the other one is holding on to the side. The one in the center gets out, the other one is, and then, because there's still a depression, it takes time for it to come up, grows to the center of the mattress. So this has time delay, okay, and spatial delay, and those are all measurable items. Okay, so they're not paired in real space, they're paired in something we call momentum space, but that's okay. Here's another analogy that breaks down. If we think of all these electrons as correlated in a single state, this is why they can get through without resistance. If you take a wheel, okay, and you roll it on a bumpy road, it'll get scattered. But if you have a big, wide wheel-based truck, okay, and you're on a bumpy road, like an SUV or something like that, you can sit there and drink coffee on a bumpy road. So they are kind of moving in step, and that's why they don't feel imperfection in the lens. Okay, correlated movement slowly. So why do we need that as superconductors? Well, I want to tell you that there's 2 reasons. One is fundamental research. We understand how those conventional superconductors work. I just gave you some analogies. We can write down the equations, and we got it. Okay? We don't know how any of the other superconductors work. And it's just a playground of broken symmetry and correlations and just things that it's just amazing to me. And we want to figure this out. So just for the simple knowledge. And by the way, this was my postdoc advisor. This proves the BTS mechanism. This here is what we call an order parameter, and they proved it. That's the graph. That's solid. But the application is like here. This is the Greene project. The Greene project is to try to get nuclear fusion energies in France, these magnets, and they use superconducting wires for that. But many exist. If you've ever been in an MRI machine, we're all enough, you get to go cool. You get to go inside of superconducting. Okay, so that's pretty cool. High-frequency detectors, cell phone filters, all kinds of research. As I mentioned before, the power grid, turbines, and superconducting magnetic energy stores. If we made better superconductors, it would be transformative. The grid has been called the triumph of 20th century engineering by the National Academy of Engineering. And it is. This is not the grid, this is actually the Eisenhower highway system, but it gives you an idea pretty much where people live. Now, if we're going to use renewables, we're going to be mining the sun here, and we're going to be mining wind power up here and offshore a little. There's been a lot of experiments on that. But in fact, the problem is that how do we get that energy to the population centers? And so the way to do it cleanly and efficiently is the power grid, because it's clean and sustainable energy carrier. But the problem and then I would say that in working with the Department of Energy, the Department of Energy recognizes the problem we have to sustain our energy future. And I just wanted to make this available on the talk. I've been involved in many of these reports, but these are, nuclear energy systems, combustion fuels, electrical energy storage. There's all these reports and they're all readable. The one, of course, I was very strong about is the high temperature superconductivity. But if there's one that you're going to read here, you can get it on these websites. And if they move this around, email me, I'll send you where it is. This one, number 13 here, is short. So we've been going since 2002 writing these reports to the Department of Energy. Then the funding got a little soft in energy research. And we wrote this one here, Directing Data Energy, 5 Grand Challenges, which is the summation of all these other basic research needs. But it was too thick. Then we wrote this one here, it was called the New Era Report. It's short. And it's believed that that is the report that funded the Energy Frontier Research Center, which I'll mention coming up here. So if you're going to read one, this is short, to the point, and clear, and I recommend it. So this is, like I said, our report from the Department of Energy on basic research needs in superconductivity. What I will tell you about the difference between the conventional and what I call the unconventional superconductors. I just told you how the unconventional superconductors, we know why they superconduct. Okay? Everything else out here, and there's many, many more that I'm plotting here we don't know. What we do know about them, and this is the focus of my research, is this is a phase diagram. This phase diagram we identified in this report, and it's been guiding the field ever since. This axis is temperature, and this axis is either doping or pressure. All of these other superconductors have this phase diagram. They start out in a state where they're either ambient pressure, they're not doped, and they're either lousy metals or insulators. If you dope them, you get this dome here. And underneath this dome is the superconductor. On the far right side of this phase diagram, we have a conventional metal, which we call serendipity. We understand that. We also understand a lot what's going on in the superconductors, but this whole area, all of these superconductors, this whole area here above PC forms this what I call electron matter. The electrons form into these tubes, or stripes, or they get huge masses. And that is my field of study. What is going on over the dome? What we know is for sure is that all of the high temperature superconductors and all of these superconductors exhibit these strange, strong electron correlations. And these correlations seem to be fighting the superconductivity, but the superconductivity doesn't exist without it. What a quandary. When I tell my high energy physics friends it makes the Higgs boson look like a walk in the park, they get it. Okay, it's really a hard problem. So let's get back to the energy aspect. For those of you that buy your Energy Star refrigerators, there's a way to go, because the amount of what we use in electrical energy in the United States is huge. It's huge. It's like 40% of our energy is used for electricity. And now we have new challenges. First of all, there's the capacity. There's a growing demand for all kinds of energy. Okay? And we are really have a problem with our reliability and the quality. Blackouts, brownouts. And this number is absolutely correct. Per year, okay, it's a little unfair because some of it's just resistance loss, and some of it is transducing the power from the coal plants to the grid, et cetera. But per year, we lose $79 billion in electrical energy loss. Okay, that's loss. So you can imagine that using superconductivity may save a little there. And I also want to point out that we expect to have 17% of our electrical energy from renewables by 2020. I'm not sure that we're going to make it. But as we add more and more renewables onto the grid, getting the solar and the wind power and the geothermal and pushing on the grid, we're going to impact the grid even more. And we have to worry about the reliability of the grid. And superconductivity can help a great deal. Now, before I go on to the more about applications, I'd like to give you a little bit of a taste of the serendipitous background here. And so this plot here, there is a low temperature physicist in the planet that doesn't have that plot somewhere in the top. And what it is the history. It's actually 103 years ago, sorry, I made a mistake on this, but 103 years ago, Heike Camelot owner made this discovery. Actually, it wasn't until April, so we're okay still. And there was a great article written in Physics Today about this. And what Camelot owner was trying to do was something called the race for the cold. All he was trying to do was liquefy helium. Okay? And he did it the same way your refrigerator works. There's a compressor, et cetera. It's exactly how the refrigerator works. He was just using high-pressure helium gas. The guy was a genius. He won. He figured it out. He figured out how to liquefy helium, 4 degrees Kelvin. That's cold. Okay? That's almost as cold as the background radiation in space. This is really cold. Okay? Serendipity. He is the technician, Giles Post, decided to measure the resistance of a metal. They chose mercury. Why? Because mercury is a liquid at room temperature, and they thought, well, it probably needs to be cleaned. So let's just see what happens if we cool down mercury. And there was your prediction. Lord Kelvin said if you go to a low enough temperature, you can freeze out the electrons, and the resistance should go up. Matheson said, oh, it'll just find a resistance that will go down to. And Dewar, who invented the door, said, oh, it will probably go to 0. Nobody predicted it. Where at a little over 4 degrees, the resistance fell precipitously to 0. Okay? And I will tell you that it was many, many years before they proved it was 0 resistance. It's hard to prove 0, right? You can say it's small. And there were many experiments. He made the first magnets, he made the first transmission lines, he did all kinds of things. And he discovered not only the superconducting transition temperature, but he discovered the critical magnetic field, that above a certain field, the material is superconducting. He also found that above, you push too much current, it stops superconducting. And there's a Chicago Tribune article in 1913 where he says that we should use superconductors for an energy crisis in the world, in 1913. Okay? So this Camelot was a man before his time. The history of that is new superconductors, we don't know how to design them. Okay? So a guy at LS who unfortunately passed away like months before I arrived at LS was Bert Matthias. And he was the guy that ran the show for many, many years. He had just mixed things together. And he was the first one to come up with a new superconductor. He took 2 elements, cobalt, which is magnetic, which you think, I told you that superconductors for magnetism. Cobalt is a ferromagnetic at room temperature. And silicon, which is a semiconductor. And he just mixes them together and, mortar and pestle and hooks them up, and he got the first weird superconductor. And he spent many years, over and over again, working on new superconductors. Never predicted one, he just tried. And he had certain rules of what made it a superconductor, and one of his rules was stay away from 0. This is, I consider, just as important as finding new superconductors. It used to be that the old type 1 superconductors, I mentioned they saw the field, they actually don't carry much current. And John Hume, who worked at Westinghouse for many years, was the first to discover, the discovery was made in the A15, but, he did find something else, was the first one to discover the A15 compound. So it's an A3B structural A transition metal, don't worry about the details. But these were the first materials that could carry supercurrents in a pretty strong magnetic field. If we didn't have these materials, we wouldn't have MRI. Okay? So if you need a really strong magnetic field, you need to use a superconductor, and you need to use these kinds of superconductors. They're still the best current carriers. Okay? So they're crucial for application. Also as important is practical wires. So John Hume at Westinghouse used a material discovered in the UK. And let me go back to this. I had to show you this is a compound. The atoms have to be in the right place. if you start, grinding it up and bending it, it stops superconducting. This material, niobium titanium, is a random alloy. You just mix niobium and titanium and smear them up together, and you get a malleable, you don't have to keep the crystal structure, and it's the most practical superconductor. So even though niobium-free germanium, the last one I showed you, has a higher CC and a higher ability to carry current and field, this is the one that we use because it's more reliable. This is the one that's used in superconducting supercollider. It's the one that's used in all the applications. It's the one that's used in our MRI. It may not be as good, but its reliability makes it the best. Okay, so if you want to say, let's make a new material, there are many factors that will make the best material. This was my boss at Cell Lab, actually did a lot of discovery of these new materials. And when he retired, my postdoc boss, which is his boss, made the statement that high temperature superconductivity discovery gets Nobel Prizes. There's about 8 Nobel Prizes in superconductivity. Nobody won a Nobel Prize for making a material that carries a high critical current, but it stays alive. So the statement is, high CC gets Nobel Prizes, high DC stays alive. So that was a great tribute to Jack, one of my bosses. Now I just want to bring in this history, and this is the way I see history. I mentioned the unconventional superconductors. These were discovered back in 1979. Franz Devlich. This material called heterochromium. Okay, it's just really weird. Here's that same phase diagram. Temperature, this is pressure, and there's that dome of superconductivity. He didn't realize it. He didn't know what was going on, but there's all this electron matter way out there. The electron mass, which you can measure thermodynamically, can be as high as 1,000 times the free electron mass. And that only comes from correlating with other electrons. Do we understand specifically why this works? No. Okay? There's lots of theories out there, but we've not coalesced on a single theory. But we do know that all of those superconductors show the phase diagram. So this was the first tunable. We see that they're tunable. And this is the first time we realized that magnetism is actually good for superconductivity, because all of those non-conventional superconductors have a magnetic position, have some magnetism in the phase diagram. And this is when we started to realize that the electron phonon mechanism, or the electron lattice mechanism, the B-step theory of superconductivity, probably didn't hold in material. And that's most of the superconductors. So then, just giving the history again, these are the ones that some people think were actually predicted. These guys don't like this when I say it, but I don't think they're really predicted. So Martin told me rule anatomy, but I still give him credit, which is, he wrote his PhD thesis that a semiconductor called strontium titanate, and it's actually more than a semiconductor, it's a hard insulator. Okay, it's a real insulator, like sand, okay? He predicted that under pressure, for a variety of reasons, this thing should superconduct. It turns out under pressure, and if you dope it, it does superconduct. His reasons were wrong, but he still claims that as a hit. Okay? Another one was that Mercury may have seen this. They were looking at another kind of effect in IBM lab in Zurich, Switzerland, and they were the first ones to discover the Couperay high-temperature superconductors in 1986. They claimed they were looking for high-temperature superconductors, and that's what they found. I read their previous papers. We disagree on that a little bit. Then, Paul Chu and Wu actually were the ones that, this was a material, TC versus time, and these are conventional superconductors. This is lanthanum, barium, copper oxide, and then these guys push it above the liquid nitrogen area. Okay, and they switched things around. It was a prediction. I could list a few other of these hits where people claim they predicted. My problem with saying that it wasn't serendipitous is these are really brilliant people, okay? And they work on this hard, full-time, studying, trying things. And they each have one hit, okay? So if any of these guys came up with a second superconductor, I would be more inclined to believe that they were predictive discoveries. So I argue that it's still serendipitous discovery. Now, this is an interesting one. This is the iron age. Cassano actually found just a few years later that a whole new set of materials can superconduct. And these are the iron-based superconductors. It was like 26 years where the only high-temperature superconductors were the Couperay. And this guy found a second set of superconductors, and Zhao, buddies in the Chinese Academy of Sciences, pushed the TC up to less than 8 degrees. Hasano says, yeah, it was serendipitous. This guy was just mixing things together to find transparent conductors. And he found that, in fact, existing superconductors. And he started working on it, and the Japanese government gave him $25 million. And then he invented the next material that's used in the most recent iPad. So that was probably money worth spending by the Japanese government. But so this was, I think, more serendipitous discovery. So again, I wanted to stress this. This is the same plot. This is TC temperature. Below this temperature, this is the TC of all these materials. That's the high temperature superconductors. And this is time. These materials in red here are the only ones we understand. Actually, I don't call PCBO red anymore. I can tell you we don't understand how we do. But these are all these materials here, and there's, probably a few hundred that we understand their BCS electron bond uncoupled superconductors. Nothing else on this plot. I couldn't plot them all. The organics aren't down here, for instance. I have identified over 40 classes of materials that have that same phase diagram, and we have yet to understand what's going on there. So it's kind of fun. Okay, so here's an example of the ubiquitous phase diagram. This is what I showed you in the heavy fermions. These are the cuprates. This is the iron base. I work a lot on that. All we have here are temperature versus doping or pressure. And these are the organics. Notice there's domes here. This is a new one, transitional bichalcogenized. These are the iron chalcogenized. There's a dome here. It's just all over the place. I can show you probably thousands of phase diagrams like this. And every single one of these cases, if you go up here, you have anything in the United States superconductors is way up here that is either called a strange metal or electron matter, but there's weird stuff happening. And why in the activated superconductors, the electrons form little sausages, little spatially separate sausages, which we call pneumaticity because they look like liquid crystal pneumatic. We're working on it. Okay. So I mentioned there are Matheson rules for regular superconductors. These are our rules. And what we know is that all the high temperature superconductors are lasers. They all contain heavy atoms. They all contain light atoms. They all have the tunable phase diagram, and in the phase diagram, they have weird stuff happening with the electrons. We have Matheson's rules to tell us about conventional superconductors. They help us classify the superconductors, but didn't tell us how to design them. We have all of these rules, but we don't know where to put the atoms down. So we still do not have predictive design of new superconductors. We just wrote a proposal where we have some new ideas, and we're working with people in computation. And I'm happy to discuss that, but we don't, so far not. Like I said, no success. But we're not going to give up. Because people put money into it, we have an international alliance. What's been very exciting to me is almost everybody is putting all their cards on the table. This is so important for our global energy concerns. And for understanding the physics, that condensed matter physicists all over the world are now working together, and we freely share ideas. I'll say, hey guys, let's meet at the coffee shop or let's meet at the bar, and we all take notes and we state our thoughts, and we're hoping that will help us understand it. Part of one of the organization I'm in is helping to fund this. And I wrote a popular article about it, how we're supposed to do this, but what can we do? So, now I want to just mention that we're kind of stuck on the fundamentals, but there's also barriers to the application. And some of those barriers are just pinning those vortices. And the inside of the vortex is normal, so on it moves to dissipate energy. You need to pin the vortices. And in our Center for Region Superconductivity, we've done a lot of work on that. In fact, one of the things which I don't have a slide here is what we've found is that injecting ions or just fast electrons through superconducting wires has been very, very helpful in pinning the vortices. And so that's been a good thing. I want to tell you about the wires that are out there and the impressive application status that exists right now. Not good enough, but it's very, very impressive. The first generation wire, which people started to do this like 3 years after the superconductors were discovered, were tubes of silver that they would pack in with a high temperature superconductor and just extrude and layer it. But it was multi-filament and very, very expensive, cheap. And the simple architecture, it wasn't thin. And it wasn't flexible, right? You come out with wire like this, if you did this to it, you could get away with that, but if you bend it like that, it stops superconducting. Over the next few years, there's a second generation wire that came out, which is a complex multi-layer structure. Better thinning, but 2% of the cross-section, I don't know how they came up with it. This is, the guys who did the applications are amazing. But only 2% of the cross-section is superconducting. Still, at the same temperature as copper, if you bring copper to that temperature, even with only 2% of the superconducting, of the cross-section superconducting, it carries 5 times the power of copper. So, we have stuff to go for, but they're just amazing. And why do you want that? So this is underneath William Street in New York City, and you can see it's a whole mass of wires, and it's just a bottleneck. If you could replace some of these wires with superconductors, you'd have a lot more room. And the Japanese are already doing that. Part of it is because they're having conduits underneath, and if they use high-temperature superconductors as opposed to conventional, it's easier to cool, and you can use the same size conduits instead of having multi-refrigeration processes. So, and also, these superconducting wires can now be made into large little systems, and one of the companies that I work with just got a multi-billion-dollar contract from Korea, because Korea is going to start putting some of these wires in ground. So as I said, 5 times the power capacity of copper, and they can relieve your bottom net. Cables operating 77K, they're ready. I showed you pictures of them. And there are in-grid demonstrations in Copenhagen, Albany, New York, Long Island, New York, Columbus, Ohio, and Amsterdam. So these have been working in-ground for many years. So before you start changing the grid around, you want a lot of finite reliability. There are still barriers to grid penetration. Okay, the cost, we still need more demonstration, and frankly, the biggest bottleneck is it's very slow to produce. And so this company, which is not American Superconductor, Superpower, they're really worried about being able to deliver what the Korean government wants in their wires. So these are some of the places I mentioned, okay? These are the power stations, and they actually did. There's a big New York cable project. The idea isn't to replace the grid. There's a couple of ideas that we want to invoke here. One is that, at least these are some of the companies in American Superconductor and Superpower, what you would do is, along with the AC grid that's going through the air, okay, so you see the wires, is buried cable that would help alleviate and just go along parallel with the existing grid. And you put a few of those in there, and you really save a huge amount and make the grid more reliable. This is my favorite. This is called Trace and Meet It. It turns out there are 3 separate grids in the United States. There's the Western Interconnect, the Eastern Interconnect, and the Texas Interconnect. I don't know the history of this, but it's true. And as you know, Tesla 1, and these are all AC, you can't connect them. They're in different phases, right? AC is alternating current. And if you just simply connect them, you will lose a lot of energy. So the plan was, and this is an ideal place to test these out because it's a short distance. Pick a little place in New Mexico where these guys meet up and convert the AC to DC, connect the grid, and then invert back up to the AC. Okay? So you go AC, superconducting DC, back up to AC, and then you don't lose the power. And this one, unfortunately, we don't have funding, but hopefully it'll bring that up again. Also, for the wind power I mentioned, you can make direct drive turbines that are 5 times lighter weight than the ones existing. Considering the turbines are being built the size of 737 airplanes nowadays, this is significant. And so one of my graduate students just got an award here in the company in Mexico where he's building these things. So it's happening slowly, but this is just a PR thing that, this is, I'll just say this, we put 62 gigatons of carbon in our atmosphere a year. Okay, and then probably that number's gone up because that's a couple years old now. We can't afford to put another molecule or atom of carbon in the atmosphere. And so rather than go this, and also use one of the most precious resources on the planet, oil. It's not renewable. This is so precious, and we burn it to heat our homes. Okay? Let's use it for things that we need it for, and let's use other power sources for heating and cooling and for other electrical support. This is Greene, can be used offshore. You've probably been reading about it now. There's a lot of wind offshore, and if we can make the turbines work offshore, then you're close to New York and LA. Okay? So these are ideas that people are exploring. It's all very exciting. I wanted to mention one more thing about the superconducting magnetic energy storage. I'm almost finished, I promise you. And that is the SMED that we're working on with Superpower, Brookhaven, and our university in Argonne. These are simply magnets. This is a technology that's existed since the 60s. You can put energy into a superconducting magnet and hold it, and then you can bring it out again by induction. It's a physics principle. It turns out if you're going to be using photovoltaics, not only do you have bright times and dark times, but photovoltaics are also inherently noisy. So one of these purposes, and there's several of these in the ground in Michigan and Wisconsin, is the idea that you pick up this noisy signal from the photovoltaic and you store it, because these things can absorb energy faster than this. Okay, they're fairly fast, they're not nanoseconds, but you can absorb this kind of energy. And then you can bleed it out to the grid when you need it. Okay? And so that's why, that's really the grid stability is one of the most important things besides just energy storage. Now, what I'm not going to do is spend much time on this, but I will tell you in my last minute is that I do point contact spectroscopy. It's a simple old measurement, and all you do is take a little tip and you touch it to the surface of the material, and it has been used to measure scattering, and what we found recently is that it's a filter for this electron matter. And so I'll show you some data. My students just left. This is in a PhD thesis, and the fact that this is up here at 177 degrees, which is way above the superconducting transition temperature, what we're picking up here and here is something called electronic pneumaticity. Okay? And we have I'm working with the theorists who were writing a paper, we've got to get out now, understanding why the point contact spectroscopy picked up this kind of electron matter, and we're really excited about it. And in fact, this is from my student's thesis, in the iron-based superconductors at the dome. These are all these data, and this electron matter goes up to 175 degrees, and this material superconductor about 20 degrees. So it's really a very high energy phenomenon in comparison. Okay, so conclusion. We still need to find other superconductors. Higher TC, room temperature superconductor would be a good thing, okay? But it also has to carry current. So a room temperature superconductor, in a magnetic field is not useful, okay? So we need better superconductors for renewable energy. And we need to understand that. When we really understand that phase diagram and the mechanism, I am certain we will then have materials by design. And I thank you for your time.
Are there any questions for our speakers? I'm also going to ask the online folks.
Yes.
Yes, the question I have is, those materials, if you have to keep at the low temperature, don't they consume, energy digestion to maintain them at that low temperature?
Yeah, so if you do the calculation, it's actually not that expensive to cool. So in the grid, they would probably use cryogen, things like liquid nitrogen. It turns out it's not that expensive. You have to, it goes in the calculation. But I would say 30 years ago, 50 years ago, it wasn't considered because the materials were expensive and we had to worry about a really cold cryogen. Now that it's cool with liquid air and the price of copper, okay, and the limits in our energy, the brownouts we're having, the lives that are lost by mining coal, in China and things like that, it becomes that, yeah, it's expensive, but if you factor in everything, it's very cheap. So if you just use economics alone and not worry about people losing energy, it's about even. Okay? But if then you calculate putting carbon in the atmosphere and the lives that are lost in these other kinds of energy production, then it becomes more important. So to me, it's a great deal.
Any other questions? I'm also not getting anything from online, so.
Basic question. Just explain to me again dosing when you were talking about. I want to make sure I understand that.
Okay, why don't we do that? So it turns out that this is the material yttrium-bearing copper oxide. That's sort of like, that's the cool-grade one, okay? If you make yttrium-1, barium-2, copper-3, oxygen-6, that's what you have here. So we have 1, 2, 3, yttrium-bearing copper. This is oxygen-6, okay? This is oxygen-7. So you're doping with oxygen. As you put oxygen in there, you start creating carriers, okay? And in these materials, it starts superconducting at about oxygen 6.4. If you keep doping even more, oxygen 7.2, 7.5, then you start getting into this area which we call typical conventional metal or standard liquid. This is the case of the iron-based superconductors. The parent material is barium, iron 2, arsenic 2. Okay? Cobalt has a different valence. So we start, and by the way, this is all changing valences. So I am being honest and doping, I'm changing valences. It's not just substitution. So if you start with barium, iron 2, arsenic 2, you're right here. Okay? And this is a material that at a certain temperature, about 135, up here it's paramagnetic and tetragonal. Below here is antiparamagnetic and orthorhombic, no superconductor. Now you start putting cobalt in here. And the cobalt replaces the iron in this case and creates positive hope, okay? And as you add, all of a sudden, you start getting some superconductivity and you keep adding, okay? And we didn't overdose, but if you overdose here, then it becomes a fairly liquid again. And so all of those materials, I don't remember the back to that stage diagram. I'm taking 75 minutes, but that's true with all those cases. And this is with pressure. So in this particular serum, copper to aluminum to whichever one it was, that's how it is zero pressure. With pressure you get a dome here, and this is the doping one. This is copper doped titanium dimelenite. So it's just starting with the parent compound, and that's going to be running our search. We're choosing chemical motif with the parent compound. If I can pick up electron matter with my point contact spectroscopy, then we go back with the chemist and start doping. Okay. And some people do pressure. Yes?
So, back in satellite, much more advanced, there is a side effect to it. Like,
I'm sorry, yes.
or side effects to the, like the 80 disadvantage
Can you say that one more time? I didn't follow.
Is there any like disadvantage? Like I know that they are very defensive a lot, but is there any disadvantage of using the superconductor?
The question was, are there any disadvantages of using the superconductor as opposed to conventional metals? Well, yeah. I mean, one thing is we're using these materials like yttrium and barium and thallium, so there's production of some of these materials are poisonous, okay? But we use gallium arsenide, and to make gallium arsenide, we need to use a lot of arsenic. So we know that we can do this safely, but that's going to be a concern. You have to cool things, so that's using energy, and that's not really very dangerous for us. So I don't know of any really negative things. I'm trying to think of them, but I think it's all great.
Okay, let's thank our speaker again. Does anyone still need to sign another sign-in sheet? There's one up front. Okay.